First of all, what are the reasons that cause JVM to crash this way? What do you think? Any ideas? Bugs, memory leaks, but bugs, why? Java is safe. Bugs in JVM, right. But can we as the programmers cause JVM to crash somehow? How? Uh, well, the most common case is the native code. When your Java application have a pieces of code written in C or any other language, you are out of JVM sandbox. And therefore, you take all the risks associated with the native code when application executes a native method. A single mistake and the application crashes. But why not to handle these situations at JVM level, you'll ask? But JVM simply can't. It has no control over the code executed in native code. There are no means to recover from these crashes. The best JVM can do is to detect such situation, collect the maximum possible information for the developer to investigate this crash, and then terminate the execution. That's what hotspot virtual machine does, and the crash dump is exactly the context of the problem. Well, but native code is not the only reason to crash. Nowadays, there is hardly a Java programmer who haven't heard about unsafe API. Like native code, it allows you to go beyond JVM protected sandbox and do whatever weird things you want, in particular to access any memory address directly. Hence, the very same problems like with native code. An illegal memory access will cause an unrecoverable failure and the fatal exit with the crash dump. Okay, even if you do everything correctly, there are still others who can be wrong. And JVM is also a product made by human developers, and like in other big projects, it contains bugs. There is a JVM bug tracker site that lists hundreds of bugs. Some are minor, some are major, and the most critical may also cause JVM to crash. The harder you exploit Java, the more is the probability to encounter a JVM bug. As you may guess, the workloads in our company are so extreme. Remember, 8,000 servers, thousands requests per second, etc., that there is a little chance that others have tested the situations like ours. That's why we tend to hit so many JVM problems. Finally, not only the software may work incorrectly, but the hardware can malfunction as well. When you have so many pieces of hardware, you should take into account the hardware issues too. Though it sounds almost impossible, but yes, we've seen in our practice a number of JVM crashes due to broken memory modules or hard disk drives. But that's too many words by now. Let's switch from theory to practice and go and let JVM crash. And a good opportunity for those who haven't seen crash dump yet. As I've told earlier, the easiest way to cause a crash dump is to run some native code. Here is a simple example that runs an integer division in a long loop. Just divide one random number by another. But the division is made not in Java, but in native method. The actual native function is as simple as this one-liner. So what's the problem with this code? Division by 0. Let's have a look. Yes, we run and immediately get JVM crash. The most important information in this fatal message is the path where the crash dump is saved. So now we can go and see what's inside. Each error report starts with a header duplicating the error message in console. This is the short summary describing what has happened and where. Here is a signal code, which is the name of OS level exception, the memory address of an instruction where the exception exactly happened, the process and the thread ID, and the JVM version. Then goes the frame, the decoded instruction address. The crash can happen almost anywhere, in a VM code, in a native library, or in user application code, which in turn can be executed either in interpreted or JIT compiled mode. Different types of code are denoted by different characters. In our case, C character stands for a native method. The address has been decoded to a name of native function plus the offset in bytes from the beginning of the function. The next block is the extended information about the exception. Along with the signal code, it contains the signal reason. An OS signal may be triggered by due to several reasons. For example, segmentation faults can occur either due to completely unmapped address or by protection violation. For example, when there is a page, read-only page, and you try to make a write operation to it. In case of memory access failure, C addr will contain the address that couldn't be read or written to. The next three sections, probably the most intricate, while being the most important ones. CPU registers. These are values of all CPU registers at the very moment of the crash. Out of here, we may extract the values of expressions, local variables, or addresses related to the instruction that failed. The stack values. The stack values are used to construct a backtrace. The stack also contains expressions and variables that couldn't fit into a limited number of registers. Finally, the raw machine code, the CPU instructions near the place of the crash. You should be a robot to understand this machine code, but fortunately there are plenty of tools to decode these numbers into more or less readable assembly code. These tools are called disassemblers, and some time ago I've discovered a nice online disassembler. You just copy and paste this machine code to the site, and it decodes them to assembly instructions. 64 bytes are decoded, 32 bytes before the place of the failure and 32 after the place of failure. And the instruction, the problematic instruction, is exactly in the middle, and the offset 32 or 20 hex. That's an example how the instructions are decoded in disassembler. And the offset 20x hex is the instruction that caused the failure. In our case, it is IDIF, which is an integer division. Well, who says that assembly is the difficult language? I tell you that it's actually the simplest one. So simple that in our St. Petersburg University, we were taught assembly by an officer at the military trainings. Seriously. Look, there is limited number of variables, registers, a limited number of operations, instructions, and all instructions are perfectly documented in architecture reference manual. So you just look at the manual and see that IDIF instruction divides silent integer in ERX register by the given register, ECX in our case. So we go back and see what was in our RCX register, and of course it is 0. So the division by 0. Okay, next goes the extended description of register values. It may be missing in some older version of hotspot. JVM helps here to decode the raw numbers to something meaningful. For example, if the value lies within heap boundaries, it is treated like a heap object, and JVM tries to decode it as a heap, as a Java object, printing its class name and its fields. The stack trace comes next. It's not actually the Java stack trace, but rather a chain of combined Java and native methods. JVM tries its best to name each frame by either a method name if it is a Java method or a C function name. This part shows you as many Java threads as were working at the moment of crash. Each lines describe one thread by its name, state, ID, and the stack bounds. A thread can be executed in either native code or Java code and be in VM code or in transition between these states. If a thread is waiting to enter a synchronized block, it will be in blocked state. Heap layout. Here is a list of all Java heap generations with all their spaces and bounds. Each space is described by 3 numbers. First 2 are the current bounds of the region, the start and the end, and the third one is the upper limit. The generations are not necessarily of the constant size. They can eventually grow or shrink during the execution. Hence the third number, the limit. But heap is not the only memory region used by VM. All generated code reside in a separate area called code cache. There goes all JIT compiled methods, and besides various VM generated stubs. For example, the bytecode interpreter is generated at VM startup, and it also goes to code cache. That's why total number of blobs is different from the number of end methods or JIT compiled methods. The next section shows the last 10 JIT compiler events. There are 2 events for each method. One is the moment where JVM starts compilation of the method. The compilation may occur in background. And the second is the moment when the JIT finished the compilation and installed the compiled code. If JVM crashes during compilation process, you'll probably see the problematic method in this compilation log. Note that person sign means an on-stack replacement. Is the moment when a method was executed in interpreter mode and eventually switched to compiled code in the middle of execution. This followed by similar sections of last 10 events from other VM subsystems, from garbage collector, from class loader, etc. I won't stop here for too long because these sections are pretty much self-descriptive. So moving on to the next very important section is complete memory map for the Java process. It lists all virtual memory regions allocated to the process. Each region is described by 2 numbers: the address range of the given region, the beginning and the end, and the memory protection flags. So each region can be either readable, writable, or executable, or all. Some regions are backed by a file. These are memory mapped files. Typically, it is a dynamic library, or a jar file, or otherwise memory mapped file. You'll also find here the stacks for all threads and heap, not to confuse with Java heap. It's native heap. The memory map is essential for finding which particular address belongs to what area of memory. if an application tries to access any address not listed in this memory map, it will definitely catch a segmentation fault. There is nothing much to tell about environment. These are basically the arguments of the program and current process environment variables. The summary of the virtual and physical memory info. If problem is supposed to arise from memory problems, then you should refer to this section first. And the model and the attribute of the processor. It is not really of much use, but we've seen some failures that were reproduced only on modern CPUs, but not on some older ones, depending on CPU features. Well, too much information. But the good news is that we are almost done with the theoretical part, and it is time for live demo. More crashes. Let's return to our example. Now we make that divisor is never 0. For example, range it from -1 to -16. Recompile and run it once again. So no division by 0 should happen. It works for some time. And what the hell? It still crashes. Any ideas why? Well, there is a crash log that will probably answer what has happened. As you see from the frame, it is still our native method, native div. The signal is still some problem with calculation. And the next usual step of analyzing crash dumps is taking instructions and decoding it with our disassembler. I did it already at the offset 20x, which is 32, is again our IDIF instruction with the divisor in ECX. Let's go and see what is in RCX register. It's -1, surprisingly, not 0. And the dividend, which is AX register. I suppose everything can read hexadecimal numbers. What number is that? Who knows? Actually, exactly. It's a negative number, integer mean value, but there is no corresponding positive number that fit 32 bits. Actually, Intel processors cannot divide integer mean value by -1. And when you try to do this, it causes the exception. In fact, JVM doesn't crash in this situation. It handles this particular case as a special case. But if you try to do this in native code, you'll get a crash. Okay, that's it with this example. Moving on to the next one. Now let's talk about how to find from the crash dump the values of arguments passed to a native method. Here I made a simple native method with 6 arguments of different types, and I pass 1, 2, 3, 4, 5, 6 as an argument. In order to force the JVM to crash, I just dereference null pointer. And here I copied the description from the OpenJDK source code, which describes which registers holds which arguments. up to 6 arguments are passed in registers. But as you probably know that GNI functions must have 2 extra arguments, GNI env and the pointer to this object. So totally 8 arguments. But we can pass only 6 of them in registers. How are the rest of arguments passed? Who knows? On stack, exactly. So let's see what will happen with our demo number 2. Of course, it crashes. We'll have a look at the crash dump. Yes, it happened in our native method. And here are the values passed. Exactly as described in our table. The first 2 are reserved for GNI. Then Java arguments are in RDX, CX, R8, and R9. So these are 1, 2, 3, 4, as expected. And the rest 2 arguments are passed on the stack. And top of stack section will help us to discover the values. And the very top value on the stack is the return address, the address of the function where we called the native function from. Okay, that's it about, that's all I wanted to say about native methods. Let's switch to another example. Now it is pure Java, no native methods, no unsafe API, just completely legal Java code. Moreover, it uses, it's not written by us, but it uses some third-party library which implements a known algorithm for substring search, Boyer-Moore text search. And what our code does is just some performance measurements running index of method in a long loop, searching for string AB in some longer string. Let's run it and see what happens. It's demo 4. Demo 4. It crashes, surprisingly. Why? Let's analyze the crash dump. Probably it will answer. We see that the problem happens in Java method. The capital letter J means that this Java method was JIT compiled. The next step, as usual, is to analyze instructions near the place of crash. We'll copy them to our disassembler. And again, in the middle of the code is the failed instruction. It is a memory load from this address to R9 register. The address is calculated as the sum of base, SI, plus index, DI multiplied by 2, plus some constant of set. The typical pattern for accessing an array. And given that we multiply the offset by 2 and the size of load is also a 2-byte load, we may conclude that it is probably an array of short or char. Let's see what's in the registers RCI and RDI. The extended information about registers tells us that RCI is an object ordinary pointer, which is basically a Java object of type character array and of the length 2. We have the source code for the problematic method. And in fact, it has 2 places with character array access. One of them is probably causing this crash. So let's go and see what is the index of the array, which should be in RDI. And the index looks very strange. It's like -1, 0 extended to 64 bits. Um, Obviously an illegal array index. But whatever index is, Java shouldn't crash. Mm, at most, it should throw array index out of bounds exception or something. So the first guess is that it is a JVM bug. Okay. Uh, we'll see the compilation events, and our guess is supported by the fact that the last method installed was the method number 4, which is exactly the problematic method indexOf. We will verify the idea by running again our test case in pure interpreted mode using xint JVM option. And now the test works perfectly. So this is probably the JIT compile bug. In the scope by restricting the compilation to all methods except our problematic one. Using the option compile command, exclude, given method. So now see that the test works in compiled mode, but with only excluded method indexOf. It is indeed a JVM bug, and it happened even on the most recent version of Java 7. It crashes on Java 8 as well. It wasn't known at the time when I discovered it, so I went to the bug tracker and posted the bug. So here this bug reported by me, as you see. Here I included the minimal test case and the initial investigation along with the crash dump. By the moment, the bug is already fixed, and the fix is going to appear in upcoming JVM update. Good news. Okay, some more examples I have today. Again, this is pure Java code. No native methods, no private API, no otherwise illegal things. It tests shared memory in Linux by writing 10 blocks to writing 10 big blocks using maps byte buffer. Shared memory, it's mapped to devshm, virtual file system. It's actually a virtual file system in Linux which holds all data in RAM. I work with shared memory like with regular files, but all data is stored in physical memory. I will run this test case, which is demo 5. It works for some time. And like all other programs today, it crashes. But we are now experts in investigating JVM crashes. We see that this time it crashes in JVM code, in libjvm. The stack trace shows that these are actually, this comes from GDK standard library methods, so it's not our problem. What's next? We can analyze the address where we tried to write and use memory mapping to find the region it belongs to. Here is the list of all memory regions. and I can find if it belongs to any of the region. And it does. So this address we try to write belongs to the memory region mapped to the file cache 8. This means that we have successfully written 7 files, but the program somehow crashed when we tried to write the 8th file. Probably something wrong with virtual memory. As I've told earlier, if there is any suspicions about memory, you should investigate meminfo. This computer has 2 gigs RAM, and you'll find that 2 of them, or exactly the half, is occupied by shared memory data. Actually, in Linux, shared memory data by default can occupy up to 50% physical RAM. The operating system supports to allocate more, but it allocates physical memory pages lazily, only when I try to write these pages. But no matter how this works on the OS level, Java shouldn't crash. Do you agree? Yes. But for some reason, it doesn't. It is also a JVM bug, which hasn't been fixed in the most recent version. But we at Одноклассники has our own fork of GDK, where we have fixed this bug. And I'm looking forward to port this bug fix back to OpenGDK. Okay, in fact, I have a few more interesting examples, but I'm short in time today. If you are interested, feel free to come to our booth and I'll show you more amazing demos and more stupid crashes or whatever. Okay, what this presentation teaches us is not to trust anybody. Even if you are a cool programmer who never makes mistakes. Actually, I don't believe in that. There will be for sure someone who make a mistake for you. I'm not saying that you should always suspect a VM bug whenever you encounter JVM crash. But if you fail to find a problem in your own code, search OpenGDK bug tracker for similar symptoms, and do not hesitate to report a new bug if you don't find an existing issue. And do not forget to include the complete crash report. Here I've summarized the steps to debug JIT-related problems. First, always try to run Java in purely interpreted mode by specifying -xint option. If the program stop crashing, then you can go on and narrow the scope by reducing the set of compiled methods using the given command line options. And finally, when the problematic method is isolated, you may either study the generated assembly code yourself by adding print assembly option, or just restrict the compilation of this method and be happy. At the end of my presentation, I would like to give you a few hints on configuring the error reporting. First of all, you can change the path where the reports are saved using error file JVM option. Person P is substituted by the current process ID. Furthermore, you can configure your JVM to automatically do something useful with error reports. For example, email it to lead developer. Alternatively, it is possible to suspend the process at the moment of the crash in order to allow to connect to it using a native debugger like GDB and debug the half-dead application right away. And finally, you can completely disable the crash report, though it may not be a good idea. And if everything else fails, just mail the error report directly to me, and it may be probably the source of for me for my next presentation. And at this point, I'd like to thank you all for coming to my presentation. I'll be glad to answer your questions right now or anytime after the conference. That's it. Thank you. By the way, for interesting questions, I will give you some nice gifts. These are thermocups. So please ask interesting questions.
Okay, may I ask one question?
Sure.
Okay, you shown an example with native code with division.
Division.
With division with zero.
Mm-hmm.
Okay, maybe it's quite trivial. Why didn't you take another example? Allocate an array in stack just automatically, 64 bytes. And assign a variable outside the array boundaries, let's say with index 50 bytes. You will corrupt the memory upward stack. How crash report will look like?
Yes, the question about more complicated cases of corrupting memory in native code. Actually, I have such examples, and I'll, due to lack of time, I'm not able to show all of them, but I will. There is a story that actually my first task when I came to Одноклассники was to investigate a problem with some crash on the production system. And what was the surprise of my colleague when I not only discovered where the problem was, but also found from the crash dump the exact ID of user that caused this crash and number of his friends and so on. So come to me later and we'll discuss the more complicated cases. Thank you. Come and take a cup after the. Well, as I've told, we exploit Java very hardly, so I have almost a feeling that we hit almost every JVM bug. Actually, many of them, maybe about 10 bugs for several years of working with Java. Yes. Yes, we have our. Not too much. Fortunately, many of the problems we've encountered were fixed already by JVM engineers. We have at this moment 3 our own patches, and 2 are specific for our case, and 1, as I've told today, I'm going to backport to OpenJDK. Okay, what?
Wasn't it better to rewrite your Java code instead of batching, instead of creating new OpenJDK?
Rewriting Java code. Mm-hmm. But yes, we can work around, but this bug in one situation, but another developer can hit the same situation in another project. So it's better to fix it once and forever. a good question. How I investigate the hardware problems from the crash dumps? Actually, it's almost impossible, but the hardware problems have the specifics that uh, they are not reproduced in one particular situations. When there is problems with a memory module or hard disk drive, your application can eventually crash at any point. So we can understand that this is probably a hardware problem if we see multiple crashes at very different places. Some in our JIT compiled codes, the others in the VM code, the third ones in with some assertions in JVM.
Regarding memory, if I may ask one more question regarding in continuation of previous
Mhm.
question. Don't your servers have ECC memory, and memory error actually it's a double bit error, which so you have to corrupt double bits. Other single bit error will be corrected by hardware, but if single bit has been corrected by hardware, you must get a log in some record in system log. Why you see memory errors at all?
Yes, it's a good question. In fact, we uh, does have memory modules with error correction, and that's why we don't see such crashes so often. But actually, the hardware problems, um, we encounter them much more often than we see the crashes. But the most of such hardware problems are detected immediately by system administrators and are fixed without involving developers.
How many crash dumps do you have during the day?
Uh,
All servers.
Not many of them. As well, if for, when we hit some JVM bug, then many servers start failing with this exact bug. But once we fix it or works it around, and we do not see another crashes for a long time. As I've told, we've hit about 10 JVM bugs for 4 years already. Yes. What question? One more question. The last question.
But if you will corrupt, can you corrupt Java heap from native code?
Sure, and there were cases when we corrupted Java heap from the native code.
It might be looks like a hardware bug when you corrupted Java heap from native code, but it's actually not a hardware bug.
Yes, you're right. This when we corrupt heap from the native code, uh, uh, the application can crash in different places, but it will be mostly Java code and mostly the methods, the hot methods that are executed most often.